Hello everyone and welcome to Part of My Take. LOL, just kidding. This is another math video and this one's about complex numbers. So, what is I? Why I? Say I rhymed, trying to be funny. Well, first, complex numbers. Those are numbers that have a real part and an imaginary part. So real numbers are a subset of the complex numbers. We learned that earlier that they're just real numbers. But when you add that complex part, and that complex part is I, the imaginary numbers, then it becomes a complex number. And we'll talk more about that later. But right now, why does there need to be imaginary numbers? So here are two questions, two math questions, two equations, each that have no solution. But we want to distinguish between the two. So let's solve both of them. We have, I don't like that, whatever, x squared plus 1 equals 0. So if we subtract 1 on both sides, we get x squared equals negative 1. And on the other equation, if we subtract 4 on both sides, we get x squared equals negative 4. Now, both of these situations are completely different, yet both of them do not have real numbers that would work and satisfy that. There's no real number you could square and get negative 1. There's no real number you can square and get negative 4. So, what mathematicians did is they came up with something called I. And I is defined as the square root of negative 1. So it allows you to distinguish between the square root of negative 1 and the square root of negative 4. So when I solve this here, ignore that part, I get x is equal to the square root of negative 4, which you factor out the negative 1, and you get plus or minus I times 2, usually written as 2i. So the reason why I was invented is to just show you that, alright, you can have no real solution, but that doesn't mean it's the same exact situation. Now if you plug I back into the original equation, I squared, since I is equal to the square root of negative 1, I becomes negative 1, and now it's a solution to that equation. Same thing with 2i. If you were to square that, you would get 4 times I squared. I squared is equal to negative 1. So you get 4 times negative 1 is negative 4. So that's why we have I in the first place. Now there's a pattern with I. I is what we call cyclical, meaning as the exponent increases by 1, the output, what I to the second, I to the third, I to the fourth, I to the fifth equal, is going to cycle between 4 different values. So I is just I, and I just put that I is equal to the square root of negative 1 to use for the next step. So to get I squared, we talked about before, that's going to be negative 1, because the square root and the square will cancel out. I cubed, now that's going to be equal to I squared times I, because of our exponent rules. So I squared was negative 1 times I gives us negative I. So whenever someone is giving you a dirty look, you'd be like, OMG, that person over there is giving me the I cubed. Get it? Negative I, evil I, whatever. I to the fourth. So I to the fourth is like I squared squared. We know I squared is negative 1, so if you square negative 1, you just get positive 1. Boom. Now back to I to the fifth. Since 5 is more than 4, we can express I to the fifth is I to the fourth times I. I to the fourth is 1 times I gives us I. So I to the fifth is just equal to I. Same way I to the sixth is equal to I squared, because we could break up I to the sixth as I to the fourth times I squared. So we get 1 times negative 1 gives us negative 1. I to the seventh is the same exact thing as I to the third, because I to the seventh is just I to the fourth times I to the third. And you get negative I. Again, someone's giving you a dirty look. Oh my god, they're giving me I to the seventh. I to the eighth. That could be written as I to the fourth squared. Power over power. You multiply. 1 squared is 1. And that is the same exact thing as I to the fourth. So in general, if you have I raised to a big number, see what the remainder would be if you divided it by 4. So anything with the remainder of 3 would equal negative I, because you can rewrite that as I to the n to the fourth, and then times I to the third, which we know I to the third is always negative I. And this part right here, I to any power to the fourth power. Actually, I should have flipped those. Sorry, this would make more sense. I to the fourth to the nth. That's this part underlined is always going to equal 1, because I to the fourth is 1 and 1 to any power is 1. Any exponent of I that you divide by 4 and get a remainder of 2, that's going to equal -1 for the same reason. Any I to any exponent that has a remainder of 1 after you divide it by 4, that is just going to equal I. And then I to the any power that's divisible by 4, that's just going to equal 1, because I to the fourth is always 1. So let's use those facts right there to try these 5 problems. So I to the 30th. What I would do is try to find the highest number less than 30 that's divisible by 4. So it would be 28. So you can break up I to the 30th is I to the 28th times I squared. I to the 28th is just I to the fourth 7 times. So we know that part's going to equal 1. 1 times anything is itself. So that's just going to equal I squared, because 4 times 7 is 28 plus 2 is 30. And we know I squared, since I is equal to the square root of -1, is going to equal -1. So I to the 30th power is just -1. Same thing with 210. So I know 4 goes into 100, so it must go into 200, and it must go into 8. So it has to go into 208. So we can break this up as I to the 208th power times I squared. And then we have I to the fourth, and 4 goes into 208, let's see, 25, 50, 52 times. So that whole part right there is going to equal 1 times I squared, and we know I squared is -1. So I to the 210th is just going to be -1. Let's try this again. So see, you're just looking for like groups of 4 i's, and they kind of just disappear because I to the fourth is 1, because that's I squared squared, and I squared is -1, because I is the square root of 1. See, it all builds off that one fact. I is equal to the square root of -1. So here, 3 times I to the 7th, we could break up as 3 times I to the 4th times I to the 3rd. I to the 4th is just 1, and then I to the 3rd is just -I, so we get -3i. Boom. -25 times I to the 25th. Again, we can break up 25 as I to the 4th to the 6th, and then you have an extra factor of I. So we get -25 times I, because this part is just equal to 1. And then last but not least, kind of like how when you're adding radicals, you can only add like radicals, so you simplify them first. When adding I, simplify each term first. So like we can rewrite I cubed as -I. Then now you can combine like terms, and you see those cancel out. Alright. One important thing when dealing with square roots, and specifically square roots of negative numbers, is to always put it in terms of I first before doing other operations. Because this rule that allows us to simplify square roots, the square root of a times b is equal to the square root of a times the square root of b, is not true if a and b are both negative. So in other words, like negative root 4 times negative root 4 doesn't automatically equal -4. What you have to do is put that in terms of I first, and then go from there. Now in this case, that'll work out, and you'll get 4i squared, and that'll equal -4. But in general, you have to be careful that you want to do this step first, where you put each number in terms of I, and then multiply. So let's look at 2 examples. So we have root 3. Well, actually, looking back at that previous example, when we had root -4 times root -4, the point I was trying to make was that you don't want to just multiply the negative 4's together and get a 16 and then take the square root of that and get positive 4. See, if you just multiply the negatives, then you won't have a negative in your final answer. So like in this case, root negative 3 times root negative 12, we don't just want to multiply negative 3 times negative 12 and get 36 and then get the square root of that and get 6, because then we get a positive answer. What we have to do is convert these to I first. Alright, so we get root 3I times root 12I. The i's are outside the radicals. So now root 3 times root 12 becomes root 36 times I squared. 6, and then I squared is negative 1, so we get negative 6. So see, if we just multiplied first, then we lose the negative. Alright, same thing if you're expanding a binomial. In this case, we should rewrite it as negative 1 plus I root 3 times negative 1 plus I root 3. So I'm expanding it to help me see the FOIL step better, and I'm also converting root negative 3 to I first, or else we would run into some sign issues. So that is the first step you want. Now we can just FOIL either using the special product, a plus b squared is a squared plus 2ab plus b squared, or just multiply it out right now. So negative 1 times negative 1 is just positive 1. Negative 1 times root 3I is negative I root 3. Negative 1, so we did those. Now negative 1 times I root 3 is negative I root 3 again. And then I root 3 times I root 3 is going to be positive I squared times 3. So now we get 1 from there, and then this part right here becomes negative 3, and then these combine to give you negative 2 I root 3. Then we get negative 2 minus 2 I root 3. Right, and that is how you want to do it. Don't FOIL it before converting all roots of negative numbers to I first. So if you see the square root of a negative number, your first step is to put it in terms of I to avoid any issues. Alright, let's just do these three real quick. So the square root of negative 3, well, here we don't need a plus or minus because the square root was already there, so we're assuming it's just positive root negative 3. So that is just going to become I root 3. Here we have 3x root negative 75a. So we write the 3 in the x. We could pull out the square root of the negative, and that gives us I. And then 75 is 25 times 3. So we can pull out the root 25 as well, and that gives us a 5. Then we're left with root 3a. So that's 75xi root 3a. I like to write the I in front of the root, because if you write it over here, then it might be mistaken for being under the radical. So any variables, everything, we want to put that in front of the root unless it's inside the root. Alright, number 23. Here, the principle of a square root doesn't make a huge difference because we're dividing and the i's are going to cancel. But just to stay true to that rule, because it works anyway, let's convert each negative root in terms of I first. So now these I over I is just 1, because that's I to the 0 power, and anything to the 0 power is 1. And then root 15 over root 3, you could divide 15 and 3, and you get root 5. So there's some work with I. Alright, so we talked about imaginary numbers. So a complex number is kind of like, every number is a complex number. And it's in the form A plus BI. Now, if B is 0, which is most of the numbers you've worked with your entire life, then it's just a real number. And if B doesn't equal 0 and A doesn't equal 0, that's what that slide should say. If A or B doesn't equal 0, then it's just an imaginary number. Or otherwise known as a complex number. You kind of use them either way. So like 2 plus 3i, 5 plus negative I, that's an imaginary number. 1, 2, 3, 4, 5, real numbers. There's no I part. And if A is 0, then it's just a pure imaginary number. So, I mean, the distinction between a pure imaginary number and imaginary number is just whether or not there's an imaginary part or not. So if you're ever solving a quadratic with the quadratic formula and you get something like 3 plus or minus I root 2, that would be an imaginary number. But if you're solving a quadratic like x squared is equal to negative 4, like the first one we did, and you get plus or minus 2i, that's a pure imaginary number. So putting complex numbers in standard form requires you to just combine all like terms and have the real part plus the imaginary part times I. So when we add or subtract complex numbers, it's just like adding and subtracting polynomials. You just add like terms. Alright, so let's do a couple right here. So again, we're just going to treat number 1 like it's 2x plus 1 plus x minus 3. So 2i plus I is just 3i. And then 1 minus 3 is negative 2. And if you remember the previous slide, you should put the real part first plus the imaginary part, and you're good. If you don't believe me, if you look back at this previous slide right here, so you got the real part and then the imaginary part right here. So put in standard form, that's how it should look. Alright, the next one, I minus 7 minus 3i minus 1. Again, let's make sure you distribute the negative, so it becomes I minus 7 minus 3i plus 1, and then you get negative 2i minus 6. Boom. Last one, we're going to FOIL. So everything's in terms of I, so we don't have to worry about the principle of the square root of a negative number. So we'll just FOIL it out. So you get 6i squared, and then 3 times negative 1 is negative 3i, and then 1 times 2i is just positive 2i, and then 1 times negative 1 is negative 1. So you get negative 6 minus 1, and then negative 3i plus 2i is negative I. Then combine that right there, you get negative 7 minus I. Got the real part, then the imaginary part. So that's the final answer. Alright, and then we also can't divide by irrational numbers or imaginary numbers. So if we have, just like getting rid of a radical that's in like a sum or a difference in the denominator, to get rid of I in the denominator, we're going to use complex conjugates when it's like an entire imaginary number with the real part and the imaginary part. We're going to multiply the numerator and denominator by a form of 1 using the conjugate of whatever the denominator is. So for example right here, we have 1 plus I. We want to square that I to get rid of it, but unfortunately we can't just square I. So instead we get creative and we multiply by 1 minus I, because we know now we have a sum times a difference, and that'll give us a difference of 2 squareds. So like a plus b times a minus b, just like 1 plus I and 1 minus I, we know it's going to equal a squared minus b squared. So this denominator is going to be 1 squared minus I squared. The numerator is just 1 times 1 minus I, so it's just 1 minus I. So we get 1 minus I over 1 minus negative 1. So we get 1 minus I over 2. And then bada bing, bada boom. You're done. Alright, and then the very last thing, solving a quadratic using I. So we did this one already, so ignore that. So here, we're going to do the quadratic formula. So it's in standard form. So we're going to do the opposite of b, so positive 2, plus or minus the square root of b squared, which would be negative 2 squared, which is 4, minus 4 times a times c, all over 2a, so all over 6. So that becomes 2 plus or minus, let's see, negative 56 over 6. Alright, and then we could take the I out, and we can also simplify root 56. Pretty sure that's 4 times 14. Yep, so that's going to become 2 plus or minus square root of 4 is 2 times I times 14 all over 6. And then now, because 2 and 2 both go into 6, we could rewrite this as 1 plus 1i, so just I, root 14 over 3. And that's 2 imaginary solutions to this quadratic. And that's because the discriminant, which I'll highlight right here and here, came out to be negative. So when your discriminant is negative, you're going to get two imaginary solutions, which are expressed right there. Alright, so I hope you found this helpful. I think this is the last slide. Yep, I'm hitting done. No other slides coming up, so I guess that is. So yeah, hope you liked the video, and let me know if you have questions in the class. Alright, have a good night.